All right, so this section 5.3 is circular trigonometric functions. Circular trigonometric functions. So that's a lot to digest, right? But after today, you'll understand what all that means. Okay. So what we're doing is we're picking up where we left off in 5.1 and 5.2. We define an angle, we define a reference angle in standard position. We're now going to talk about a reference triangle. A reference triangle. So before we look at that, let's just come down to example 1, because I want to draw this for you first. Let's say that I have an x and y axis. We're going to basically take what you did in geometry, and we're going to translate it now to a coordinate plane, which means that this is now going to be coordinate geometry instead of Euclidean geometry. So give yourself a nice x and y axis, and we're going to use it several times, so you might want to copy it and paste it. All right. Let's say that I have an angle theta that terminates in quadrant 1, all right? So remember that we have an initial ray that starts on the positive x-axis. So if I rotate somewhere into quadrant 1 and stop, I'm just going to draw that terminal ray almost on a 45-degree angle. Okay, now you can draw it wherever you want, so long as it terminates in quadrant 1. Notice we didn't even draw the initial ray, did we? We don't need to draw the initial ray because it's always the positive x-axis. So in this case, this angle is theta, but this is the reference angle, isn't it? We talked about the reference angle being the positive acute angle that's formed between the terminal ray and the closest x-axis is central, okay? And in this case, theta ref is actually equal to theta, okay, because they're both positive and acute. Now here's what we're going to do, something a little bit different. We're actually going to go to some point on the terminal ray, and I'm just going to draw a point there, and we're going to drop a perpendicular, drop a perp, as I call it, to the closest x-axis. That's called an altitude, okay? When we do that now, we create a right triangle, okay? A right triangle, and this is what we call the reference triangle. Oops. This is what we call the reference triangle. Now notice the reference triangle has the reference angle as its central angle, or the central angle is the reference angle, okay? So now, once we have a right triangle formed by dropping a perpendicular down to the closest x-axis, we can start talking about the side lengths, okay? So opposite my reference angle, I have the side O. Adjacent, I have A. And then the hypotenuse is H, right? So that's how you labeled all three sides in geometry: opposite, adjacent, hypotenuse, O, A, and H. Now, it was important when you were drawing O and A specifically to remember which one was the reference angle. Because if we're not on the coordinate plane, remember, you could also have this one up here. This one could also be the reference angle. This one, though, it is not the reference angle. But in geometry, it could have, right? In geometry, you didn't have the coordinate plane. So that one could have been the reference angle. Now, why is it important to know which one's the reference angle of the two acute that are not the 90-degree angle? Because what happens to your opposite and adjacent if you refer to the other angle? They switch, right? They switch. So we don't have to worry about that, because for us, the reference angle is always the central angle. Central means close to the origin. It's always going to be that one. So our opposite is always going to be the vertical. Always going to be the vertical component. And the adjacent is always going to be the horizontal component. And the hypotenuse is always the distance from the origin to that point, right? There's the hypotenuse. It's always opposite the 90-degree angle. All right? So there's your reference triangle. Let's go ahead and define it specifically then. A reference triangle is formed by dropping, quote unquote, a perpendicular. Dropping a perp, like on a crime show, dropping a perp is when you chase after a bad guy and you tackle him, right? Dropping a perp. That's what we do. It's really called an altitude. From the terminal ray to the standard position of the standard position angle to the x-axis. Okay, again, we draw it to the x-axis. So we don't draw a horizontal line to the y-axis. That'll create another triangle. It's not the one we want. Okay. The reference triangle is always dropping a perp. Let gravity do the work, okay? Dropping a perp. Now, let's go ahead and look at what happens if we terminate in quadrant 2, okay? We're going to do the same diagram. So we can choose independently where to stop. I chose independently to terminate in quadrant 1 for the first example. Let's do terminating in quadrant 2 and see what that looks like, all right? So now we'll use the same color scheme. I will take my angle starting on the positive x-axis, and I'm going to draw it somewhere in quadrant 2. Now for me in quadrant 2, I think I want to draw it not at a 45. I think I want to draw it just a little bit flatter. It doesn't really matter. As long as it ends in quadrant 2, if you want to go closer to the y-axis or closer to the x-axis, that's up to you. It doesn't really matter. But now, if I drop a perp straight down, boom, this is my reference triangle. It's right here. Now notice theta gets me to the terminal ray, but in this case, is the reference angle equal to theta? No, the reference angle is here. So we've already done this diagram in the other section, 5.1, but we're going to do it again. We are primarily concerned initially with finding the reference angle. And we need to be able to do it if we know theta, okay? So if we do it in degrees, we're stopping short of 180 degrees, so theta is smaller. So it's going to be 180 degrees minus theta degrees, if theta is in degrees. We're not going to use degrees very often, so let's do it in terms of radians. 180 degrees is the same as how many radians? Well, 2 pi, careful, is all the way around. Halfway around is single pi, right? 3.14. So it's going to be pi radians minus theta in radians. So that's how we find the reference angle. It's going to be important that you draw the picture, because if you have the picture, you kind of know what to do, right? We're stopping short of the x-axis, which is pi, so pi minus theta. Okay, now again, if you look opposite the reference angle, you have O, adjacent, and horizontal. So again, notice that the opposite is still the vertical and the adjacent is still the horizontal. That's going to be consistent, because the reference angle for us is always, always the central angle. Okay, quadrant 3, same idea. If I terminate in quadrant 3, let's see what that looks like. I'm going to draw one now that kind of rotates and finishes closer to the y-axis. Okay, somewhere right in there. And now notice if I drop a perp, I'm actually dropping a perp upwards, okay? But you could think about it as dropping a perp straight down. Boom. Oops, that didn't work so well. We have the ability to snap these straight lines, so we might as well use them. Nope. Nope. One more time. Here we go. Come on, big bucks. Big bucks, no whammies. There we go. So notice in this case, because my angle terminated closer to the y-axis, I have a triangle that's taller than it is wide. But this here is the reference angle. Okay? And the angle theta in blue that gets us all the way around is like between 270 degrees, or 180 degrees and 270 degrees. So how do we find the reference angle now if we know theta? Now we've gone past 180, right? So which is bigger, theta or 180? Theta, okay? So it's going to be now theta degrees minus 180 degrees if you are in degrees, or theta radians minus pi radians. Okay, the reference angle is not the distance between the terminal ray and the y-axis. Nope, it's always between the x-axis. So we're always working off like 0, pi, or 2 pi. All right, now notice again, if that is the reference angle, the opposite is your vertical, and the adjacent is still the horizontal, and your h, your hypotenuse, is really the distance from the origin to that point on the terminal ray that you dropped it from. Okay. Now, if we terminate in quadrant 4, this is the last one that actually creates a triangle. Let's go ahead and draw a generic one in quadrant 4, and I'll go back to drawing it on a 45, just because it kind of gives you more room to label, which is really the only benefit. So there's theta. It gets me all the way around. I drop a perp from anywhere. Now, It doesn't matter where you drop the perp. Let me show you why. If I drop a perpendicular from here, I get a small right triangle. If I drop a perpendicular from here, I get a bigger right triangle. If I drop it from here, I get an even larger right triangle. But because these three triangles that I'm drawing share two side lengths and the reference angle, they're all proportional to each other. Would you agree? They're all dilations of each other. What do we call those triangles that are just magnifications, stretches, or compressions of each other? If they're proportional to each other, they are similar. Thank you. These are all similar triangles, okay? They're all similar triangles. So it doesn't matter from where you drop the perp, okay? The reference angle is going to be the same in any case. So I'll just use the big pink one just because, again, it gives me more room to label. So theta reference now, how do we find it? Well, we're stopping short of a full rotation. So now it's 360 degrees minus theta degrees, if we happen to be in degrees. Or if we're in radians, what's a full rotation in radians? 2 pi. So 2 pi minus theta. And then now opposite the reference angle is still your vertical. Adjacent to your reference, or reference angle is the adjacent A. And the hypotenuse is, again, the distance from the origin to that point you dropped your perp from. That's H. All right, so if you understand these 4 scenarios, then you're going to be in good shape moving forward, okay? Now, there are other cases. You can choose or independently choose to stop on one of the axes, right? What do we call those angles that land on the X or Y axis? Like 0, 180, 270, 360 degrees. Remember the word quadrantal or quadrantal angles? Quadrantal angles. Those are going to be kind of special cases because if your angle terminates on the x-axis, you don't have a triangle at all. Because what you've done is you've collapsed the height down to nothing, okay? And if you terminate on the y-axis, you have no triangle because now you've collapsed the width down to nothing, all right? So those are the special cases where you collapse the triangle down. So we technically don't have a reference angle. We technically don't have a reference triangle. So those are special cases. And we'll look at those independently. All right, so now that we have all 3 of these, let's go ahead and define what a trigonometric function is, all right? A trigonometric function, or sometimes I call it a trig ratio. Of course, trig is short for trigonometric. A trig ratio or a trig function. This is like what you talked about in geometry. Y'all learned SOHCAHTOA, right? SOHCAHTOA? Easy to remember. So SOHCAHTOA was an acronym for remembering 3 of your trigonometric functions. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent was opposite over adjacent. When you had your reference angle identified. Ours is always going to be the central angle. So that actually is 3 of the 6 trig functions. There's 6 of them, okay? Now, what is a trig function? Well, let's look at sine. Sine was so that meant you wrote it like this. Sine of theta is the opposite divided by the hypotenuse. In any triangle, you have 3 sides. So what is a trig function? It's nothing more than the ratio of 2 of the 3 sides of the right triangle, the reference triangle, formed by dropping a perp from the terminal ray based upon your independent choice of angle, theta, in standard position. So every function, if you want to write this here, every function has an input and an output, right? Y equals f of x, that's how we read that. Remember, x is your, that doesn't show up very well. X is your independent variable. It's your input. Okay, and then f of x itself, or y, that's your dependent variable, which is your output. So I used the example of a function earlier in the year about buying pomegranates, remember? I go to the H-E-B, I'm determined to get myself some healthy foods for once. I can independently choose anything I want. So I choose on my own, uncoerced by anybody, to buy 2 pomegranates, okay? You're not going to talk me into buying an orange. You're not going to talk me into buying 3 pomegranates. I independently choose to buy 2 pomegranates. That's X. That's my input. Now that I've chosen that, the output depends upon my input. Now I go to the register and the price depends upon what I chose. Okay, so I expect there to be one price and one price only for those two prime graphs. So the output depends upon the input. So we have an input and an output. For your trig ratio, it's the angle that's your input. You can stop anywhere you want. Okay, we can rotate around and stop in quadrant 1, 2, 3, or 4, or on the axis itself. We choose independently where to stop. But once we stop, and where we stop, we now have a triangle whose side lengths depend upon that, right? As you can see, if I stop closer to the x-axis, my adjacent is going to be bigger than the opposite. It's going to be wider than it is tall. If I stop closer to the y-axis, now the length of the height, the opposite, is going to be larger than the width, the adjacent. So the output depends upon the input. So when we look at this trig ratio for SOHCAHTOA, it's this right here that's your independent variable. And the ratio itself is your dependent variable. And that's all a trig ratio is. A trig function is nothing more than the ratio of two of the three sides of a right triangle. So never forget that. We're going to be using sine, cosine, and tangent quite a bit in here. And I never want you to forget to remember that when we talk about a sine, cosine, or tangent value, it's nothing more than the ratio of two of three lengths of a triangle. That's it. Take any two of the three, divide one by the other. If you do them in that particular manner, you have yourself a sine ratio, a cosine ratio, or an adjacent ratio. Okay? All right, now here's the deal. We're going to shift from opposite and adjacent and hypotenuse to using different variables, namely x and y. This is not planar geometry. This is going to be coordinate geometry. Let's write that down. Coordinate geometry. So we've already talked about this. We're going to be putting our triangles on the coordinate plane, the Cartesian plane. So we're going to be using x's and y's to navigate through those two-dimensional space. Right, Ethan? Right, Ethan? Yeah, hang in there. Okay, so here's what I want to do. I want to redraw an angle that terminates in quadrant 1. So I think I still have my x and y axis there. So let's do this. I'll make it a little bit bigger. And we're going to label this one slightly differently. So let's go ahead and again and draw a terminal ray that terminates in quadrant 1. Boom. And I'm going to draw it on the 45. It gives me more room to work. So there's my angle theta. And we know then that the reference angle, in this case, is also equal to theta. They're one and the same. If theta is already positive and acute, then so is the reference angle always, and they're the same. Now, I'm going to drop a perp from, well, I'm just going to go out as far as I can here with my diagram. I'm going to drop a perp from right there. And again, it doesn't matter. You're going to want to be able to label your triangle, so don't draw it so close to the origin. Why wouldn't it snap? There we go. I'm not real good at that. There we go. So there's the right triangle. So I always like to draw the little right angle symbol there, the little box in the corner, because it helps me identify the interior. So that bottom central angle is our reference angle always, not the one in the top there. Okay, so now here's what I'm going to do. To get to this point in two-dimensional space from which I drop my perp, I go from the origin here, and it looks like I'm going to go right and up. Would you agree in this case? That's going to give me a coordinate x, comma, y. And in this case, we know that x is going to be positive and y is going to be positive. Yes? We go right and up. Okay, now, this distance here is nothing more than your x value. And this distance here, the height, is nothing more than the y value. So instead of using the opposite, we're going to use y. And instead of using the adjacent, we're going to use x. Now this here, instead of using h for hypotenuse, and it still is, we're going to use little r. Why little r? What do you think? X and Y makes sense because to get to that point, I go right and up, go right X value, up Y value. If I were to take that point X, Y, and instead of stopping at theta, what if I were to continue rotating all the way around? What shape would it make? It would make a circle, right? And the hypotenuse ends up being the what of that circle? Radius. R is called the radius of rotation. And it is always positive. Okay, it's always a positive number. So it's a length. Okay, the radius is always positive. But X and Y can be negative. X and Y, though, may be negative. They can be. In this case, they're not, because I'm going right and up. In quadrant 1, X and Y are both positive. So now what we're going to do is, since I have all three sides of this right triangle, if you want to help yourself here as a crutch, you could draw this as H, O, and A, right? So you can fall back on SOHCAHTOA, maybe initially, but we don't want to do that, okay? The Y is always the opposite, the X is always the adjacent, hypotenuse is always R. Let's go ahead and list the ratios, all right? So if I take any two of those side lengths, leave some space over here, let's go ahead and list the ratios. Can anyone give me one of the ratios? Take any two sides and divide them one by the other. R over H? Is that what you said? No, we're gonna use X, Y, and R. We're gonna use X, Y, and R. We need to start retraining our brain to think in radians and to think in terms of X, Y, and R. Well, let's just do the sine ratio first, since I already mentioned sine, right? Sine is opposite over hypotenuse, so SOHCAHTOA, opposite over hypotenuse. So that would be for us Y over R, yes? Y over R. So let's go ahead and list that one. That's Y over R. And we know what that one is. That's sine. So there's sine. The full name for sine is SINE. That's the name of that ratio. All of these ratios are going to have names that someone decided long ago at a naming party, perhaps. I wasn't there for the names. But this ratio, whenever you take the vertical measure to the radius or the hypotenuse, you get the sine ratio, always. Okay, and we abbreviate that SIN, and we put theta. Okay, so just to show you here, just to reiterate, theta is your independent variable, and the ratio itself is your dependent variable. Okay, your input is theta, your output is the ratio. Let's just keep going. SOHCAHTOA. The ka in SOHCAHTOA meant that cosine of theta was adjacent over hypotenuse, yes? What would that be in terms of X, Y, and R? X over R, yeah. So we have the cosine of theta equaling X over R, and we call that the cosine. So really, it's the same name as the first guy, sine, but he has a co in front. And the co means something very special that we'll learn later on. It means cofunction. Right, Ethan? Yeah. So we got the sine ratio and then the cosine ratio, which we abbreviate COS of theta. It's always your horizontal to the hypotenuse. And then TOA, the tangent part, meant that tangent of theta was the opposite over the adjacent. And in terms of X, Y, and R, that's what? Opposite over adjacent is Y over X. Yeah. So let's list him down here. Tangent of theta is Y over X. And we abbreviate it TAN of theta, but its full name spelled out is the tangent. So those are your three main ones: sine, cosine, and tangent. SOHCAHTOA. Here's something that helps you remember. Sine and cosine are very, very important because they're the only two ratios that have R in the denominator. They're the only two, okay? So you can't take a ratio of one to itself, right? So it can't be R over R. And because they both have r in the denominator and r is the hypotenuse, then the other two are the short legs, right? So these are always going to be less than 1. You can't have them being greater than 1, because if these ratios are greater than 1, you're saying x or y, one of the short sides of the triangle, is bigger than the hypotenuse. And can that happen? The hypotenuse is the biggest side. So these guys are always going to be greater than 1 in magnitude, I should say, in size. Okay, they're always going to be greater than 1. Now, why? Again, because r is the hypotenuse. Because r is going to be greater than x and r is greater than y. Okay, it's the hypotenuse. So that's 3 of the ratios. Do we have any more ratios? Can anyone think of any other ways to take 2 at a time? Y over r, x over r, y over x. Are there any more? These are the 3 main ones. What about r over y? Is that a unique ratio? If y over r is like 3 over 5, I'm sorry, y over r is 3 over 5, then r over y would be 5 over 3. That's a different number. So leave some space over here. Oops. Let's come over here and leave some space in the front. We'll call that r over y. And that's just the what of y over r. Not inverse, but they're the reciprocal trig functions. Yeah. The reciprocal trig function. So the reciprocal of x over r is r over x, and the reciprocal of y over x is x over y. Now these guys also have names, okay? And it's not sine, cosine, and tangent. So the name that we give to r over y is this, cosecant. And we abbreviate it as CSC of theta. Cosecant. So you probably haven't heard that term before, okay? Because SOHCAHTOA is what you had. The reciprocal of cosine, r over x, is going to be called the secant ratio, and we abbreviate that SEC, like the Southeast Conference, of theta. I use lowercase for the 3-letter abbreviation. You can use uppercase if that's more comfortable. And then we have the reciprocal of tangent, x over y, which is cotangent. And anyone want to guess what we abbreviate cotangent? 3 letters? COT. Good. Cot of theta. So it's important when you list these out that you do have the theta. If you just write cot equals, that's incorrect. If you just put cosine equals with no theta behind it, that's incorrect. Theta is your independent variable. The ratios themselves are the outputs, the dependent variables. So there's 6 ratios. Are there any other ratios that we haven't listed yet? Does anyone see a different ratio of 2 of those sides to the third one? Or do we get all of them? We got all of them. If there's only 3 sides, we're looking for permutations 3, choose 2. If you have three objects and you're taking them 2 at a time, it's a permutation because order matters. It's sometimes written like this: permutation of 3, choose 2, or it's sometimes written as this: 3 permutation 2. It ends up being 3 factorial all over 3 minus 2 factorial, which is just 3 factorial, which is just 3 times 2 times 1, which is 6. That's what factorial means. That exclamation point means factorial. It's used a lot in discrete math or probability, even statistics. It's a way to account. So this is a permutation. Permutation is where order matters. So you have 3 people in a group. There are 6 different ways to assign offices. Like you got the president, the vice president, and then just some loser, right? Oh, that hurt. There's 6 different ways you can assign 3 people those roles, right? But if you're just trying to form like a team of 3 for something and the order doesn't matter, that's called a combination. In a combination, it doesn't matter. You have 1, 2, 3, 2, 1, 3, whatever. They're all the same. You just have a group of 3. That's a combination. These are permutations. So there's only 6 ways then to take ratios of 2 at a time. And we found all 6 of them. And now we know their names, right? So there you go. You need to memorize these. Now, notice there are only a couple things here. Notice there's only 3 names. Do you see that? There's really only 3 names, and then they're cos. They're co-functions. So we have sine, secant, and tangent. Sine, secant, and tangent. But then if you put cos in front, cosine, cosecant, cotangent. We get their co-functions. Now, unfortunately, and this is the second thing I want to point out, unfortunately, co does not mean reciprocal. Okay? I'm going to write that down. Co does not mean reciprocal. Now, it just so happens that tangent and cotangent are reciprocals of each other. But that's a coincidence, okay? They are also co-functions of each other, and we'll talk about that further down the line. In other words, the reciprocal of sine is not cosine. And the reciprocal of secant is not cosecant. But here's what you can remember. Tangent and cotangent, that does work. Tangent and cotangent are not just co-functions of each other, they're reciprocals of each other. So that leaves the other 4. No 2 cos go together, okay? So you have sine and cosecant, and then secant and cosine. They each pair up with a co. A non-code name pairs up with a code name. So what's the reciprocal of sine? Cosecant. And what's the reciprocal of secant? Cosine. Okay, so cosine and secant are reciprocals of each other. So this is why you really only learn SOHCAHTOA in geometry, because really, if you have all 3 sides, you have all 6 trig ratios. It's just a matter of listing them. But if you have sine, cosine, or tangent, then you know they're reciprocals as well. So it's a lot easier to work with sine, cosine, and tangent. If you've ever inspected your calculator, the TI-84 family, you notice there's a button for sine, cosine, and tangent. But there is not a button for secant, cosecant, and cotangent, because you don't really need it, right? Because they're just the reciprocals of these other 3. So memorize these in terms of x, y, and r. Now notice they are still the same. If you look at tangent, tangent is y over x. That's TOA, right? So notice it's still the opposite over the adjacent. So try to get away from labeling them as OA and H and using that as a crutch. Try to flat out remember them in terms of x, y, and r. And r is always positive, where x and y can be negative. All right. You ready to use them? Try them out. Before we do, let me help you remember one thing. I don't know if this will help you, but if you write the word sine, that sounds like y and it sounds like height. They all have the I sound. I, the long I sound. Sine, y, height. People have told me that when they get done with my class, they sometimes have nightmares, and that's the sound they hear in their dreams. It's kind of an annoying sound, but it helps you remember. Sine, y, height. Right, Kenzie? Kenzie, you up? Kenzie, yeah, good. Sine, y, height. The sine ratio has the y in it, okay? It measures the relative height of your reference triangle with respect to the radius. Sine, y, height. The cosine is the x, it's the width. That doesn't quite rhyme, right? Cosine, x, width, those don't really have the same thing. But the cosine essentially does measure the width of the triangle with respect to the radius. So sine and cosine are very, very special. Again, they're the only 2 that have a magnitude less than 1. They're the only 2 that end up being what you're going to see continuous for all real numbers. And they measure the relative height and width, sine and cosine do respectively, of your reference triangle. Okay? Sine, y, height, sine, y, height. All right, let's try it out. There's the formal definition. Oh, by the way, these are called circular trig functions, and I think it's pretty obvious to see why. The radius is your radius of rotation, and if you were to go all the way around, it would generate a circle. So these 6 trig functions that we just listed, sine, cosine, tangent, cosecant, secant, cotangent, those are all called circular trig functions. If you take higher level math in college, like Cal 3 or Cal 2, and maybe even some other advanced algebra, you might get into hyperbolic trig functions or elliptical trig functions, okay? Because they are out there. We're just going to stick with the nice round circle, okay? All right. So the types of problems are that you're going to have on the worksheet and on a quiz, right? A 4-question quiz that I'll put in today during D-Lunch. It's going to be due on Thursday at 8:50. The types of questions on that quiz are what I call the 2 clues problems. 2 clues problems. Now, the 2 clues sounds a lot like Blue's Clues, right? Blue's Clues, used to watch that show. That was like Dora the Explorer. We shout at the television, and you're hoping that you affect the outcome of the show, right? And Steve hosted it, right, until he went to college, which there were a lot of rumors why he left, but it wasn't quite the same. 2's Clues problem. So it's kind of the same thing. Blue's Clues. You're going to be looking for clues to help you answer these questions. And I'm going to give you 2 of them. It's just a matter of you identifying them and using them correctly, okay? So you're going to have, let's just write this out here since we're recording. You're going to have 4 quiz questions that are like this, in addition to the worksheet that's going to be due on Thursday, the 25th. Oops, Thursday the 25th. Dang, March is almost gone already. Of 2021 at 8:50 a.m. Okay, I'll make a folder for that in Canvas. So pay very close attention to what we're about to do. You will need a calculator, but we'll pull that up when we get there. All right, y'all ready to go? 2's Clues problems? We're doing great on time, by the way. We've got an hour still. Here we go. Example 3. If sine of some angle theta, if sine of theta, that's how we read that, is equal to 5/6, that's your first clue. This is clue number 1. Clue number 1. And theta is between 90 degrees and 180 degrees. That's clue number 2. Now that's a huge clue. That's a hit you over the head, shove it in your pocket, here's the clue kind of clue, right? What we're going to be interested in is drawing those little pictures that we drew above. We need to identify where does theta live, in which quadrant does it terminate, so we can draw an appropriate triangle, okay? This tells us that the angle theta lives in which quadrant? 2, right? This flat out tells us it's between 90 degrees and 180 degrees. That's not always going to be given to you. Okay, there's going to be a more sneaky way to tell. But right now it's the first one. So we'll just take the clues as they come. So go ahead and draw yourself your little X and Y axis. I still have mine on my clipboard. Now what we're going to do is we're going to use clue number 2 first. It doesn't matter what order you use the clue. And I'm going to draw a generic terminal ray, a generic one, out here in quadrant 2. Oh, yeah, okay. Now, from there, I'm going to label this as theta. Okay, make sure you label that as theta. I don't know what theta is, but it puts me in quadrant 2. From there, go ahead and drop yourself a perp from a convenient point on the axis, enough so that you make a triangle that is easily manageable, okay, so that you could draw in it easily. All right, so now let's identify the reference angle. This is my theta subscript ref. That's your reference angle. It's not equal to theta. Here's what the instructions are going to ask you to do. Find the simplified exact value of the other 5 trig functions of theta. Okay, I have one of them given to me. I have the sine ratio. I need to find the other 5. And then it says to find theta and theta ref using the calculator. Okay, so here's how we're going to use the second clue. They're telling me the sine ratio of that angle theta that puts me in a quadrant 2 independently. They tell me that the dependent variable, the ratio itself, is 5/6. Now remember, 5/6 being a ratio represents what in the triangle? It represents 2 of the sides. Good. So let's remember then which sides were given. What is the definition, as we'll say, of sine of theta in terms of x, y, and r? It's y over r. Yeah. Sine y height. Got it? Sine y height. So sine is y over r. Now, if you look at the triangle here, it's still going to be the opposite over the hypotenuse. Okay? But let's go ahead and label it. Here is your x, here's your y, here's your r. Now, just before we actually assign numbers to it, let's just look at the sign. To get to this point, x, y, in quadrant 2, I have to go left, don't I? So what do I know about x? It's negative, right? And y, because I'm going up, is positive. And of course, r is always positive. But notice x is negative. That's interesting. In geometry, you can't have a side length of a triangle that's less than 0, right? A negative side length doesn't make sense. And it still doesn't make sense to have a negative length. But x and y are vectors. They're directed distances, okay? So telling me that the ratio of sine being 5/6, I know that y is 5 and r is 6. So I can come up here and label those now. Y is 5 and r is 6. And I know y has to be positive 5 because I'm going up. And of course, r has to always be positive. That's 6. Now, here's the deal. If I know all 3 side lengths, I can list all 6 trig ratios, right? It's just a matter of putting them and naming them correctly. So here's your next task. Once you draw the picture and you identify the quadrant it lives in using the 2 clues, draw your triangle and you label the given sides, you're going to have to find the 3rd side. You're going to have to find the missing side. And how do we do that? Is there a geometric formula or equation that relates 3 sides of a right triangle? A squared plus b squared equals c squared. That's the what theorem? The Pythagorean theorem. I'm not going to spell out Pythagorean or theorem. We're going to use the Pythagorean theorem. Now, it is a squared plus b squared equals c squared, but a, b, and c are just arbitrary letters. That's how you memorized it. We're going to use it with our variables. So for us, it's going to be x squared plus y squared equals r squared. Okay, got that? X squared plus y squared. X and y are the 2 short lengths. X is always the horizontal, y is always the vertical, and then the radius of rotation is always the hypotenuse. Let's plug in. Let's plug in what we know, okay? So we're going to get x squared plus y is 5 squared equals r squared, which is 6 squared. You didn't need parentheses there, but I put them. And now we just need to solve for x. So we get x squared plus 25 equals 36. So x squared equals 36 minus 25, which is 11. And now when I solve for x, by taking the square root of both sides, what must I better remember to not forget to do, Kenzie? Hang in there. Plus or minus. I'm going to list them as 2 separate things. So x either equals the negative square root of 11 or the positive square root of 11. And it's real easy to mess up your trig ratio simply because you forget a negative. We always consider both plus or minus. Sometimes one of them is not relevant, but we always consider plus or minus. Which one, if any, do we want there? We want the negative one, right? Because we are moving left. Now, 11 is a prime number. If I could simplify the radical, I would. But 11 is a prime number, so it's just negative square root of 11. And that looks weird to call the length of a triangle negative square root of 11. Not because it's the square root of 11, but because it's negative. So you got to remember that x and y are vectors. The negative tells you to move left, and the positive tells you to move up. So that puts you in quadrant 2. So if you wanted to, you could list the coordinate of this ordered pair as negative square root of 11, comma 5. That's equal to x comma y. Yes, yes? Sure, right? And if you move your point further out, the point would change, but it would just increase or decrease by a scale factor, okay? And what would happen to the scale factor when you divided it out? In other words, look at the sine ratio. If I make this triangle twice as big, 6 times 2, 5 times 2, square root of 11 times 2, what happens if I take the sine ratio now? The sine is still going to be the y value, which is 2 times 5, over the hypotenuse, which is 6 times 2, what happens with your scale factor? It divides out. It's the same. So that's why when you're doing trig ratios, 2 sides to the third, it doesn't matter where you drop your perk from. If you simplify your trig ratio, regardless of the size of the triangle, the trig ratio simplified is always going to be the same. Your scale factor will always divide out. Okay. But now that I have all 3 sides, and let's not forget that my sides were not times 2. Okay. It was just 5, 6, and negative square root of 11. Now that I have all 3 side lengths, I might as well just get rid of the 2's. Okay. I have all 6 trig functions. So let's go ahead and list them. So let's come over here and create a new column. Here's what I want you to do. Get in the habit of doing this. Let's list your SOHCAHTOA first. Okay, so sine of theta, cosine of theta, tangent of theta. Okay, and if you want, in the beginning, you can put the definition behind them. Sine is y over r, cosine is x over r, tangent is y over x. If it helps you to write the definition in terms of x, y, and r, that's fine. And then list the reciprocals in the next column. The reciprocal of sine was what? Do you remember? Cosecant. So it's r over y. The reciprocal of cosine is secant. It's r over x. And the reciprocal of tangent is cotangent. Memorize these, memorize these, memorize these. Okay, if you write out the definition, this is optional, okay? This is optional. And I would recommend that you do it in the beginning. Writing sine of theta equals or secant of theta equals, that's not optional. You have to do that, okay? Now, let's just go ahead and pull the ratios from the triangle. Okay, that's what we're going to do. We're going to be pulling the ratios from the triangle that we've already labeled. So let's go ahead and see what sine is. Sine is y over r. So for us, that's the vertical over the hypotenuse. That's 5 over 6. Is that what was given? Yeah. So if I compare it to what was given, did I get the same answer? Yes. So that's a check to make sure you've done it correctly. Now, if I give you one of them, I'm not going to take off in your final list. This is your final presentation for you. I'm not going to take off if you don't list the one I gave you, because I already gave it to you. But it's nice to have the complete set right here, all right? Now, what's the cosine ratio? Well, cosine is x over r. That's negative square root of 11 over 6. So negative square root of 11 over 6. Now, notice how I wrote that. I wrote the negative in the top. Is that okay? That's actually preferred, isn't it? Because I can clearly see that it's the x that's negative, but you have to be careful, because if I gave you that ratio, this could be the square root of 11 over negative 6. Or it could be negative out front, square root of 11 over 6. If you have a negative ratio, it's because either the top or the bottom are negative. So if you were kind of working backwards, like if I told you the cosine ratio is negative square root of 11 over 6, you would have to realize why it's negative. Because it's x over r, and r is always positive, it has to be negative because x is negative, right? So I don't care how you write it, as long as it's simplified, okay? And the square root of 11 is completely simplified. Okay, let's keep going. Tangent is y over x, so vertical over horizontal, that's 5 over negative square root of 11. 5 over negative square root of 11. Now, here's what I do want you to do. I do want you to rationalize your denominators. Oops, I can't spell denominators. How about just denoms? In general, it's okay to have a radical on the bottom. There's nothing bad about it. It has to be simplified radical first, and this one is. But there's a reason why we want to rationalize our denominators, and it's going to involve what we do in the next lesson. By the way, I scheduled Mr. Cortez to be in here to observe me next Thursday, so he'll be in here. Just keep doing what you're doing. If you have any questions for him, make sure you ask him, okay? He's in here as an observer, but if you have a question for him, feel free, right? Interact with them. They like that, okay? If we have time, maybe at the end I'll have a little short race story so that Cortez can see it. If he doesn't get bored and walk away sooner. I don't know. He may be like, ugh, man. Okay, so what does it mean to rationalize our denominators? No radicals downstairs, okay? No radicals downstairs. So what I'm going to do is multiply by the square root of 11 over the square root of 11, right? And we get in the top -5 square root of 11 over 11. That's the ratio. Okay. Now, why is the ratio negative? It's because which one is negative, x or y? It's because the x is negative. We know that. Okay. But notice y itself could also be negative. If we have an angle that terminates in quadrants 2 or 3, y could be negative as well. So you have to understand that just because you have a negative listed in the top, it doesn't mean that the top number is the negative number. Right? If the ratio is negative, it's because one of them is negative. All right, so you don't even have to show this step here. This step is also optional. You should be able to rationalize in your head. And if you want to just go, from one to the next, that's fine. All right, now we can list our reciprocal ratios. And here's what I would recommend. Rather than just flip the ones we've already written down, get them from the triangle and make sure they are the flipped version. So cosecant is r over y. That's 6 over 5. So 6 over 5. Is that now the reciprocal of 5 over 6? Yes. Secant is r over x. Pull it from the triangle. That's 6 over negative square root of 11. 6 over negative square root, 6 over square root of 11. Is that the reciprocal of negative 11 or square root of 6? Yes. Now, is this where we want to leave that one? No. So now, if we in our head multiply by root 11 over root 11, we get negative 6 root 11 all over 11. And that's what I mean, you could do it in your head. And notice I kind of naturally put the negative in the top. That's okay. If the ratio is negative, we know why. It's not because the R. R is always positive. It's that perpetually sunny person that's in your life. Hopefully you have one of those if you're not that person yourself. Always positive. And then x over y, that's going to be the negative square root of 11 over 5. Negative square root of 11 over 5, and now we compare it. Is that in fact the reciprocal of 5 over negative square root of 11 before we rationalize? And the answer is yes. So there they are. There's all 6 trig functions. Yay! Got it. That's not that bad, is it? You got to memorize your definitions. Okay, so now here's the next thing. Now, I want to find theta and theta ref. Okay, and notice that we are in degrees. We're in degrees first because it's easier. So I know that my angle has to be something between 90 degrees and 180 degrees. Well, how am I going to find theta? Well, I just created 6 equations with one unknown. See that? You can now treat your trig ratios as conditional equations with one unknown. The unknown is theta, right? So here's the deal. You can choose any one of those 6 and solve it for theta. Okay? Choose any one of the 6 and solve for theta. In theory, you can choose any one of the 6 trig functions and solve for theta. Now, what I would do is choose either the sine, the cosine, or the tangent. Why? Because we're going to have to use our calculator. And the calculator has these buttons. All right, so even though we listed the cosecant, secant, and cotangent, I'm not going to really choose those to work with, okay? No offense, right? Those are those eccentric people in your family that like, hi, and then you sit in the corner at Thanksgiving and don't talk to them, like, they're strange. They're there, they're interesting. We're not going to, not going to diss them. They're right there. So choose sine, cosine, or tangent. So I'm going to choose either 5 over 6, negative root 11 over 6, and negative 5 root 11 over 11. And it doesn't matter which one you choose. So just based upon these numbers, which one of those 3 would you probably use? Probably the sine, I hope you're thinking. And it's for 2 reasons. One of the reasons is 5 over 6 itself is what compared to the other two ratios? It is positive, good. The other two are negative, so I like to work with positive things, not negative things. That's a good reason. I wasn't thinking about that. I was looking at they don't have radicals, right? Radicals are kind of like, radicals. So if we can help it, maybe I'll stay away from a radical. But the third reason now, which is kind of more important, we calculated the cosine and tangent ratio, didn't we? If we had accidentally messed up, if we thought that this was a Pythagorean triple, if we thought it was a 4, 5, 6 right triangle, and we labeled x as -4, all 5 ratios that we found would be wrong, wouldn't they? And you don't want to use wrong information to help you find more information, right? So another reason why we're going to use sine is because we didn't find it, rather it was what? It was given, so we know it's correct. So you can catch a mistake, right? So that's good in practice. So you want to show me which one you're using. So let's go ahead and write it out here. I'm choosing the sine ratio of theta, and it was 5 over 6. 5 over 6. By the way, if I gave you that the cosecant ratio was 6 over 5, I would still use the sine ratio to be 5 over 6. Because even though they didn't give me the sine ratio, it's a lot easier for me just to flip a number than to use the Pythagorean theorem and find a number, okay? Now, how do we solve for theta in here? Yeah, it's a good question. I have theta trapped behind a sine ratio right now. How do we unsine something from both sides? Well, if it were multiplied, we would divide both sides by whatever, right? Because division undoes multiplication. If it were added on one side, we would subtract it from both sides because that undoes addition. What is the inverse operation of taking the sine of an angle? Well, it's called the inverse sine. Okay, and we write it like that, sine to the -1st power. It's kind of like this notation, right? We read that as F inverse. It's reserved for that sine inverse, or sometimes it's called arc sine. We'll get into that later. Same thing. All right, so here's what we're going to do, and I'll show this in this step here. If I take the inverse sine of both sides, it's an operation, so unlike multiplication and division or addition and subtraction, it has to go in the front. It has to go in the front. So I get this and this. I took the inverse sine of both sides. See that? In purple. Now look what happens on the left side. What do you think the inverse sine of theta is? What happens if you compose two inverse functions back to back? What do they do to each other? Multiply by 5 and then divide by 5. Add 7, subtract 7. We're right back where we started, right? So if I start with theta and I sine it and then I unsine it, which is inverse sine or arc sine, I should be left with right back what I started with, which is theta, and we are. They undo each other. Inverse functions undo each other. And we're left with theta equals the inverse sine of 5 over 6. All right, so we've solved it for theta. Now, that's not a very fulfilling number, but it is an exact number. The inverse sine of 5 over 6 is some angle theta. Now, this is why these problems are so fun. I need to go to my calculator now. Your calculator is only going to give you one answer, and it may or may not be the one you want. If I'm the one doing it, it won't be the one we want, because I'm going to make you work a little harder. So let's pull your calculator up if you haven't already. Grab it. Remember, if you're using the emulator, you can find it under Corpy's World under other maths. It's the hidden link. You got to reload your ROM file, unfortunately, every time. So hopefully you have downloaded it to your iPad. And let's see if that worked. Yeah, it worked. Okay. Now here's the deal. Your calculator, when you reset it, or when it comes out of the package, it's always default in radian mode. So if you go to the mode button, okay, your mode button is right there in the top left corner. Scroll down to like the 5th row or the 3rd row. For me, it's the 3rd row. See how it says radian and then degree? We're in degrees right now. How do we know we're in degrees? Our second clue told us we were in degrees, right? So I need to switch over to degree mode and hit enter. Now, generally, it doesn't matter if you're in radian or degree mode unless you type in one of those buttons, okay? And notice right there above the 7, 8, and 9, 2 units above, 7, 8, 9, I have sine, cosine, tangent. We're about to press one of those buttons. If you ever press one of those buttons for any reason in a calculation, you need to be aware of the mode you're in, because the calculator will interpret it based on what mode you're in. So I want to be in degree mode, so now I'm going to go back to my home screen. Second mode, remember, quits. Now I'm going to type in exactly what I have here. I want to see this on your paper. I want to see it solved for theta. Now, if you want, you could skip the purple step and go straight here. That's fine. I just showed you that it worked, okay? But I do want to see it solved for theta. Now, all we have to do, since we are in degree mode, is type in the right side, inverse sine. Now, how do you think you get inverse sine? Second sine. Notice right above the sine, it has sine in blue to the negative first. Second sine. That's not the reciprocal of sine. Okay, that's cosecant. This is the inverse sine. We're switching the input and output. You take the inverse sine of a ratio to get an angle. You take the sine of an angle to get a ratio. Inverse sine of 5 divided by 6. Close it up, hit enter, boom! And your calculator tells you theta is 56.442 ... degrees. Okay? Now, you look at your diagram. You always have your diagram drawn first. Where does 56.442 live? Quadrant what? 1. Crap! Okay, this is the calculator's answer. It gave me this theta to be 56.442 ... degrees. Is that the angle we want? Does 56.442 live between 90 and 180? No. But guess what the sine of this angle is? The sine of this angle is the same as the sine of the angle that I have. So why in the heck is the calculator giving me that answer? Well, maybe it just doesn't know that I want it to be in quadrant 2. So let's go back to the calculator. If you hit second enter, it recalls it. Okay, let's try it again. I'll type in inverse sine of 5/6, but this time I'll say, give me the angle in quadrant 2, please, and I'll hit enter. And crap, it gives me the same one. Let's try it again. Second enter recalls it. Maybe you didn't hear me, Mr. House. Maybe you didn't hear me. So if we yell, Mr. House, inverse sine of 5/6, give it to me in quadrant 2. Dang it. It still gave it to me in quadrant 1. Do you think the calculator is ever going to give you the answer in quadrant 2? No. Because it is in function mode, right? If you go to mode, notice it says funky down there on the 4th row. We're in function mode. So why is it only going to give us one output when we type in an input? Because that's what functions do. I'm taking my 2 pomegranates to the register. I'm not going to get 2 outputs. I'm going to get one output, one price. But here's the deal. Your calculator is always going to give you enough information to find the one you want, okay? So look at this. I know that I told the calculator to give me the angle, where is it, over here? Give me the angle whose sine is positive 5/6. It's greater than 0. Remember, sine is y over r. So r is always positive. So the reason sine is positive is because y is positive, yes? Would you see, would you agree? This is why you need to know the definitions. Sine is positive when y is positive. In which 2 quadrants is sine positive in? Well, in which 2 quadrants is y positive in? Quadrant 1 and quadrant 2. Y is positive when we're up above the x-axis. So you just told your calculator, give me an angle in quadrant 1 or 2 whose sine is 5/6. Your calculator gave you the one in quadrant 1 instead of the one in quadrant 2. Why? Because quadrant 1 is easier to get to, right? But notice, this is what's true. This must be 5, and this must be 6 in this other bizarro reference triangle, yes? Those two triangles now that I drew in quadrant 1 and 2, guess what? They're not just similar to each other, they're the same actually, right? If I just take the triangle in quadrant 1 and reflect it across the y-axis, I get the other one in quadrant 2. You see that? They have the exact same measures. Exact same measures. In fact, this one, remember when we found x by the Pythagorean theorem? It said x could be plus or minus the square root of 11. Well, in this bizarro reference triangle, it's the other one. So here's the deal. Your calculator will always give you enough information to find your reference angle. Okay? Let's do that. Let's write that. The calculator always gives you enough info to find your reference angle. Don't expect the calculator to give you the angle you want. You're actually, most of the time, going to find the reference angle first. We just have to play detective now. So here's the deal. What are the same about those triangles? Well, not just their lengths, but also their angles, right? Their angles should be the same. They're not just similar triangles. Similar triangles always have the same angles. The side lengths are just dilations of each other. These are not even dilations. If you think about a reflection, maybe we have a negative dilation, but the angles are the same. So if this angle right here is 56.442, guess what this angle over here is? It's also 56.442, which is the what of our triangle? The reference triangle. So, this is actually, I'm just going to put theta ref on here. I'm actually going to answer theta ref is 56.442 or 56.443. I don't care if you round or truncate. Theta ref is 56.442 degrees or 56.443 degrees. Now, once I know the reference angle, can I find theta? Yes. Go back to your picture. My angle theta stops 56.442 degrees short of the x-axis, which is 180, yes? See that? So now I will say theta equals 180 degrees minus 56.443 ... What do I put the ... for? It keeps going. And I do not want to use the truncated number 442 or 443. My answer is up there. It's the previous line. So if I just do 180 minus the answer, which is second negative, 180 minus, let's try that one again, 180 minus second negative, I get it. It is 123.557 degrees. Is that an angle between 90 and 180? Yes. Now, here's how you can check your work. Let's store this. You know how to store this? Right above on, there's a stow button. Hit stow, and let's do alpha A. Hit alpha A, enter. And now if I called it A on my calculator, I'm going to call it capital A on my paper. I want to store it with all its decimals. Here's what you can do. Your calculator gave you 56.443. We found 123.557. That should have the same sign value as 56.443, which means it should be 56. So let's try it. Let's plug it back in other words. Let's plug it back in. What is sine now of that answer? Well, I'm going to do alpha A. Oops. What is sine of alpha A? I get 0.833333333, which now if I hit math enter, enter, and convert it back, I get 5.6. Yay. The calculator didn't give us that, and it won't. The way I write these questions, it's never going to be as easy as just taking the answer the calculator gives you. But here's the deal. The calculator will always give you an angle whose reference angle is the same as yours. Let's write that as well, okay? It's an addendum to this. The calculators the calculator's answer and your triangle, which is your angle theta, I should say in your angle theta, not triangle. The calculator's answer and your theta have the same reference angle. Always. Okay, so if it's not the one you want, it just comes down to, can you find the reference angle of the angle the calculator gives you? If you need to draw the calculator's angle so you get it in the right quadrant and then find the reference angle, that's fine. But once you have your reference angle in hand, you then go back to your diagram and you can find your angle. Okay. Now notice, let's choose one of the other two before we move on. Cosine or tangent. Since your calculator has those buttons, you could have chosen either one of those. Let's try the tangent. Okay. If I choose the tangent equation, tangent of theta is -5 root 11 over 11. Let's go ahead and take the inverse tangent of both sides. It's kind of the same idea. Inverse tangent of theta is just theta, and we're left with inverse tangent of -5 root 11 over 11. Now, let's type that into the calculator. I'll go over here to the calculator, let me turn it on, and I hit second tangent now of -5 square root of 11 divided by 11. And I didn't use the horizontal division bar because we're only dividing by 11. So it's a little bit faster this way. Make sure you click out of the radical when you put divided by 11. All right. So boom, I get -56. Let's draw that. According to the calculator, what angle or what quadrant does its angle live in? Quadrant 4, good. I go down because it's negative 56.442 degrees. Well, what would be the reference angle then of the calculator's reference triangle? Wouldn't the reference angle be positive 56? Yeah. Okay. So in this case, the calculator gives you a negative angle. The absolute value of that answer is the positive acute angle. So guess what? Now that I know that times a -1 is a way to do that, now that I know that that's my reference angle, I go back to my picture and I'm like, oh, now I'm stopping that much short of 180. So again, I do 180 minus the answer, and boom, you get 123. Okay. So why did the calculator give me an answer in quadrant 4? Okay, well, let's see. If tangent is y over x, tangent is negative when either x or y are negative, right? Tangent is negative when either x or y are negative, one or the other. So it's either going to be -x positive y or positive x negative y. What two quadrants does that put us in? Well, -x positive y puts us in quadrant 2, right here, where we want to be. Or positive x negative y puts us over here. So tangent is negative in those opposite quadrants, 2 and 4. The calculator didn't give you the quadrant 2 angle. It gave you the quadrant 4 angle. Okay, now notice it didn't get to quadrant 4 by going all the way around, did it? The calculator is programmed to be efficient. So it got to quadrant 4, not by going all the way around, but rather by going straight down to it clockwise. All right? And so that's how tangent works. Now, just for comparison, let's say you chose the cosine. You know, you might have. Let's choose cosine of theta to be -√11 over 6. So we write that down. And now what I'll do, I'll take the inverse cosine of both sides. So I'm left with theta equals inverse cosine. They all look the same way. The inverse trig function just has the little -1 exponent looking thing, okay? Now before I do this, let's try and predict where the calculator is going to give me an angle. Remember, this is your cosine ratio, it's x over r. And because it's negative now, since r has to be positive, it's negative because x is negative, right? Which two quadrants is x negative in? There's two quadrants where x is negative. quadrant 2 and 3, right? X is negative in quadrants 2 and 3 when we're to the left. So the calculator is either going to give us this angle here, or it's going to give us this angle here. We'll call this theta sub 2 for quadrant 2, or theta sub 3 for quadrant 3. Which one do you think the calculator is going to give us? Based upon what you've seen so far, the calculator is very efficient. It likes to get to the closest quadrant, and it likes to get to the closest quadrant in the quickest way. What's closer to get to, quadrant 2 or quadrant 3? They're really the same, aren't they? One rotates clockwise, line them out, and the other one rotates counterclockwise. So do you think if there's a preference, it's going to give you a positive or a negative angle? It's going to give you a positive one. If it has a preference, it's going to give you a positive one. The only time it's going to give you that negative one is if it's in quadrant 4. It doesn't want to rotate all the way around. So which quadrant should it give us based upon that loose criteria? It should give us the quadrant 2 angle. Is that the one we want? Yeah, that's the one we want. So let's try it out. Inverse cosine, so second cosine of negative square root of 11. Oops. Negative square root of 11. Click to the right, divided by 6. Boom, 123.557. That actually gave us the angle we wanted. Oh. So if we know that, we could have chosen cosine to begin with. But guess what? Now we still need to find the reference angle, don't we? And the other two, we kind of found the reference angle first. It doesn't matter which one you have first, you can always find the second. So now, if I know that my angle gets us to here, now the reference angle is just its difference between that and 180. So I know that the reference angle is now 180 minus 123.557 ... degrees. And I'll just type that in, 180 minus the answer, and boom, you get your reference angle. So in the end, I don't care which one you use. I don't care which one you use. In some cases, you're going to find the theta first, and in most cases, you're going to find the reference angle first. If you know one, you can get the other by working off the x-axis. All right, so choose either sine, cosine, or tangent. I just showed you that any one of them will give you the answer. It's not necessarily true that using inverse cosine will always give you the answer you want, okay? That doesn't always work that way. Now, here's the other reason you need to have those definitions memorized in terms of x, y, and r. You need to know, based upon a trig ratio, which two quadrants it can live in. And there's always two, right? R is always positive. So you either can memorize this chart, which I wouldn't do. There's like a way to do it with your fingers, like they teach that at Canyon over there. They like to use their fingers, I guess, you know, for figuring things out. You don't need to memorize this or use your finger trick. Just know that R is always positive, but X and Y can be negative. So if you know the definitions in terms of X, Y, and R, you've got this chart figured out. Now, why is that important? Let me start the next question. I don't think we're going to get that far, but I want to make sure if you want to start the quiz that I'm going to post during D-Lunch today, because it's due Thursday, you can. Notice in this one, we're going to do the same thing. We're given two clues. Now we're given that the tangent is 5/12, but now we're told that the cosecant is negative. Cosecant of theta is negative. That's a more esoteric, not direct clue. Now, here's what we want to do. In this case, we're going to go ahead and draw an x and y axis, and we're going to look at the first clue. You can look at the first clue. Cosecant is negative. This is the same. It's listed as the second clue, sorry. But last time it was the first one we looked at. So the order doesn't matter. But I'm going to look at this. Cosecant is negative. Now, what's the definition of cosecant in terms of x, y, and r? This is why it's important. Cosecant is r over y. You got to have that memorized. R is always positive. So if the cosecant ratio is negative, it's because y is negative, yes? And now look at this. Draw your little coordinate plane. In which two quadrants is y negative? 3 and 4, right? Cosecant is negative when y is negative. That's below the x-axis. It's that easy. You don't have to memorize this chart up here. That tells you cosecant is negative in quadrants 3 and 4. Okay? You don't need to memorize that because you know what the definition is. Now, notice that gets you into one of two quadrants. I still need another clue, dang it, to get me into one of those two. Well, enter the tangent ratio. Tangent is y over x. Now, when you have the tangent or cotangent ratio, it's either y to x or x to y, which both can be positive or both be negative. So tangent is positive when you have a positive x, positive y, or they could both be what? Negative. Tangent is positive when x and y are the same signs. What quadrant does that put you in? Well, let's come over here. I'll choose a darker shade. Positive x, positive y puts us in quadrant 1. And where does negative x, negative y put us? Quadrant 3. Now, what's the only overlapping quadrant? 3. That's the only quadrant that satisfies both. So we know it has to be in quadrant 3. See how that works? That's kind of fun. That's why I call it a two's clues. You need one trig ratio so that you can generate numbers, but really all you need is the sign of another trig ratio. And that'll pinpoint. So each of those two clues, and this is more like what I'm going to be doing, each of these two clues will put you in two quadrants. If you know your definitions in terms of x, y, and r, it's going to be the one they have in common. Okay, so now let's go ahead and draw ourselves a generic terminal ray over here in quadrant 3. I'll drop a perp, and now I'm going to label my sides. Tangent is y over x, so that's 5 over 12. Now, if you label that as 5 over 12, the tangent ratio is going to come out to be 5/12, but is that correct? This is what students tend to miss. And it's easy to miss because, again, in geometry, you had to have positive lengths, right? But we're doing coordinate geometry. So to get to that point down here in quadrant 3, I have to go left 12 and down 5. So they're actually both what? They're both negative. That's why it's so important for you to draw that picture. If I don't see the picture, you're not going to get credit. Now I need to find the hypotenuse by the Pythagorean theorem. So let's do that. Negative 5 quantity squared plus negative 12 quantity squared equals r squared. So that's 25 plus 144 equals r squared. So r squared equals 169. Is that a perfect square? Yes, that's 13 squared. So I always consider both positive and negative. Do I want either one of those or both of those here? What do we know about the radius? It's always positive. For x and y, it's super important to consider negatives because they can be negative. But in this case, we know the radius is 13. And now, of course, if we know all three sides, do we have all 6 trig ratios? Yes, so let's go ahead and list them here. Sine of theta, cosine of theta, tangent of theta. Let's list those first. I'm not going to write out the definitions this time. Sine is y over r, so that's negative 5 over 13. Boom. Cosine is x over r, that's negative 12 over 13. Tangent is y over x, that's negative over negative, so it's positive 5/12. Is that what they gave us? Yep, so we verified. Now we do the reciprocals. Cosecant of theta, secant of theta, cotangent of theta. Always in that order, and don't forget your theta. Cosecant now is r over y, so that's 13 over negative 5. That is the reciprocal of the sine. Secant is r over x, so that's 13 over negative 12. That does end up being the reciprocal of cosine. And cotangent is x over y, so that's going to be positive 12 over positive 5 because the negatives divide out. Now we'll stop right there, but we'll pick up tomorrow or Thursday. You have enough information. Does the announcements come on, don't they? Yeah. You have enough information. From here, it's real easy. You could choose any one of these. I would probably choose the tangent one. Take the inverse tangent, figure out where that calculator angle lives. Find the calculator's reference angle. That's going to be the same as yours. And then all you got to do is come over here and do 180 plus the reference angle, okay, to find that angle theta. to get you over there. Okay. So again, look for that 4-question worksheet. It'll be due Thursday at 8:50. I might give you all more time. In fact, let's see. I'll make it due Thursday at 4:20. Here's why. I want to make sure we have a chance to work. I wanted to get through example 6 today. Okay. You have perfectly enough information to both start and finish. But we didn't get to finish out example 2. But from here, it's the same as, or 4. From here, it's the same as example 3. I will work through this example to finish on Thursday. I'll work example 5 and 6 on Thursday when Mr. Cortez is in here. And then you'll have till 4:20 that day to finish. So that gives you another lunch and a power hour to finish it, okay? But you should be able to finish it now based on what we did. You just have to know the definitions in terms of X, Y, and R. And then also on Thursday, once we finish this, we're going to get into the unit circle. You might have heard rumors about the unit circle in Precal. We're going to develop it. I'm going to show you what it's used for, and that'll be something that you're going to have to memorize, and we're going to quiz every class period on that for a while. Okay. Any questions before we stop the video? All right. Thanks for being here.